C compiler for LLVM, okay? It generates intermediate representation from C. I guess that since Gentauro, the people that are sitting with you are also functional people. Okay, because for a second I was scared. GHC also generated LLVM code in the past for Haskell code. I'm not sure if that is the case anymore. And it's something like that, but used for C. So let's talk about obfuscation techniques. Well, the most relevant author in this area is Shenxi Wang. But of course, there is prior research from other malware developers. That's the main purpose of these techniques. And the main objective of obfuscation is obviously making the intentions of the programmer unclear. So now that we have gone over the boring stuff, let's talk about real stuff. Control flattening. Who of you has ever had to defeat control flattening before? Okay, I guess that you have been fighting some malware probably before. Okay. Well, control flattening is a really simple transformation. The idea is that you make all your code go back to the central node, and then on that central node you will decide where you will go to afterwards, which, well, it's basically a spaghetti code brought to the maximum expression of it. Let's talk also about constant obfuscation. The idea is reasonably simple. If you have a set of constants and you don't want your users or your reverse engineers or your attackers to know what they are, you can encrypt them, you can make arithmetic operations that will generate those constants, you can place some of the constants on memory and then get them back. And I will talk about how I implemented this on LLVM. Opaque predicates have a pretty similar purpose. The idea is that the predicate will always result on the same value or on the correct value, but it provides the value in a way that is hard to get. For example, if you added 2 to an integer and then subtracted 2, you will always get the same value that you got originally, but you will get that value in a slightly harder way to see. Register swapping is one of the most simple, well, actually polymorphism techniques. The idea is that if you have 2 registers and the operation is commutative, you can just swap the registers so that the 2 operands will be in the reverse order. Dead code insertion is also a really good technique to, well, mess up with reverse engineers. It basically means that you will put a lot of dead code into your code, and if you are using also something like control flattening, you are going to make a shitload of fun, because that means that all your invalid code will also be hanging from exactly the same place as the real code that will be executed. So you will have a hard time figuring out which is the real work that the program is going to do and which is the path that it's going to follow. And finally, we have code reordering. This technique, as far as I know, is, or was better said in 2015, a little bit more novel. And it's mostly based on how processors work when they do out-of-order execution. What we implemented basically was a way to keep track of the dependencies of an instruction inside of a basic block, and then schedule one of the instructions randomly, so you could have one of the many possible programs that will result on the same code or on the same execution path. So let's talk a little bit about control flattening. Control flattening is a really simple technique when you want to implement this on LLVM. The first thing that you need to do is have a very big phi value. A phi value is basically an instruction that, depending on where the code comes from, will choose one value or the other. And then you use that phi value in order to choose a value that you have assigned to each one of the different basic blocks of your function. And you use a switch in order to decide to which function do you want to jump. If you want to do T7 better, you can map conditional branches into select blocks, so you will choose one value or the other. So the basic idea is that you just assign one integer to each one of the basic blocks of your function, and then you choose the value based on where you are coming from and the result of, for example, a select before. And finally, just branch based on that code to the specific function that you want to go to. It's not that complex when you see it like that. I really hope that none of you has to go over my code ever. It's awfully hard to implement. I spent like 3 days trying to get this one to work. Let's talk about constant obfuscation. This is a lot simpler. So basically, we choose each one of the constants, and we decide randomly whether we want to obfuscate it further or not. We have two different techniques. One of them is basically arithmetic obfuscation. For example, adding a number, and then you will have two constants, one which is +2, and then the constant that is 2, for example, and or replacing them by access to global memory. The reason why we decided to implement the second one is because adding memory accesses for constants can make it really hard, especially when your constants are split in smaller values, for example, with a string of text. So once we have the resulting constants and the operation, we can decide to go and re-obfuscate everything again. If we re-obfuscate everything, then we have to be very, very careful not to end up in an infinite loop or a really long loop that will cause a stack overflow and kill the compiler. So usually we don't enable constant re-obfuscation. If you want to do so, I strongly recommend any value with a probability over 1/2. Because with 1/2, basically you have around 1 in 1 possibility that, in average, that you will keep re-obfuscating everything forever until your loop is broken. Okay. Let's talk about BB-split. BB-split was a simple transformation I made in order to make the obfuscating my code even more fun. And it's really simple. If you have a normal function, you will find that you only have basic blocks ending at conditional branches or unconditional branches, as in all the functions all the instructions on the basic block will be totally linear, and the branch is what will finish the basic block. So the problem is that on a normal function, you might end up, for example, with as little as 2, 3, maybe 5 basic blocks. If you want control flattening to work out properly, it's better if you have, say, 20, 30 basic blocks, because then it's a lot harder for the reverse engineer to figure out what each one of these basic blocks was doing. And that's exactly what we do here. Basically, we use the site to split basic blocks at some random point in order to increase the number of basic blocks and make the reversing task a lot harder. This is one of the most simple transformations that you can make, and it's probably the best way to start working into your own obfuscation framework if you want to do this with LLVM. As a matter of fact, I think that was actually the first one I implemented. Then you can also randomize the order of the basic blocks, and against what you might think, this actually works really well because the assembler will process each basic block individually. So the result is that instead of having a completely linear code, except for the flattened control function at the beginning, you will, for example, have the control flattening function, then you might have the function that the part of the code that executes the function, then you might have one of the if branches here, then you might have a full switch in there, then at the end another the else branch, which makes the control flattening a lot more efficient because before you had a completely linear set of basic blocks being issued, and now you will have a completely random looking set of basic blocks. The most important thing when you implement this is that you have to be very, very careful because if I recall correctly, LLVM expects the entry point of the function to be the first block. If you want this to be even more efficient, you can also ensure that the entry point of the function is always a branch so that you don't have any initialization code at the beginning of the function. Okay, let's talk about the next one, and that is randomized instruction orders. So this is probably the hardest transformation of all the ones I had to implement. Basically, I used something similar to Thomas Sulo's algorithm in hardware in order to decide in which order I was going to issue the instructions. So what we do here is that we pick all the instructions inside a basic block, and then we try to figure out which are the dependencies of these instructions with the prior instructions in the basic blocks. So once we know all the instructions that have no dependencies, we choose one of them at random, and then consider that that instruction is issued, so all the dependencies from that instruction are deleted. And then we can recalculate and find other instructions that have no dependencies in order to decide which is the next one that we will issue on the next step. This basically results in pretty random code because inside a basic block, you might have 5 or 6 different things going on at the same time. And by doing this, we basically manage to interleave the code. The best thing is that since internally processors will also work this way, you actually can have a very, very small performance decrease by applying this transformation. And if you did this in a slightly different way, as in trying to maximize the number of instructions that can be executed on parallel, you might even find out that your performance in your program gets significantly increased by applying this kind of transformations. And finally, we have, reordering of functions. That's pretty much the same as with basic blocks. There is no specific dependency or anything like that. You just need to be careful that the first function of your module is the start function, or the function that will execute the code. And well, same thing for globals, obviously. And let's talk finally about operation swapping. So here is a really fun fact. You know, if you have been working with LLVM, you probably know that you have an infinite number of registers. But when you have to map that into hardware, you usually have a limited number. If I recall correctly, it's 16 for 64-bit AMD architectures and 8 for 32 bits, for example. So that means that when you are mapping those original registers into the resulting registers of the hardware, the order in which they are inside the function might result in them being mapped to completely different registers. So that is why we implemented this specific operation. It's one of the dumbest operations possible. Basically, you have a list of whitelisted functions that are known to be commutative. And if you want, that's chosen randomly, you just swap the operands so that the first operand will be taken first, and the second will be taken last, or you just leave them as they are instead. So this transformation actually results in pretty different code when you try to compile code that is being used with it. And that's basically the first part of the talk. That's the hard theory. Now I'm going to explain you why I did Altistit and how you can actually use this in order to make your software releases a little bit more interesting. So the idea behind one days is reasonably well known. Once you release a vulnerability patch, you can just figure out what the patch is doing and then try to figure out what the exploit is so you can exploit it. That's, for example, what happened with Bluekeep. So the problem we have is that compilers will always generate the same code for the same inputs, well, mostly. In fact, it's actually an ongoing effort to make GCC always generate exactly the same code for the same input, so that, what? Yeah, there is actually an ongoing effort to do exactly that, for example, with GCC, so that you can have, what's it called? Probable compilation, and you can make sure that the code that is compiled by a third party is exactly the same code you will get, and that there was basically no magic or anything weird being done behind. That means that the amount of changes on the resulting binaries will also be small. If you just change one function, most likely the only change or the few changes will be on exactly that function and not anywhere else. That is a problem because it makes it really easy to go and figure out which of the functions are the ones that have been changed, and therefore where the buffer overflow was fixed, for example. So let's suppose that we can generate code pseudo-randomly, and we still get this really nice thing of reliable compilations and compilations working exactly in the same way. But we have a magic key that you need in order to have the compiler behave on exactly the same way. If you change the key, then the compiler will behave differently. And that is basically the idea. Basically, we use a cryptographic pseudo-random generator that is seeded once per function and once per module with the key that we will provide it. If you use the same keys, you will get exactly the same results. If you use different keys, when you apply the obfuscation transformations, you will get different results because You will probably notice that when I was talking about the obfuscation transformation, that when I was talking about the obfuscation transformations here, you will see that there is a lot of choose. For example, choose if we want to obfuscate a constant, choose a technique, decide whether we want to re-obfuscate. All this has to be chosen randomly. So we can use a pseudo-random number generator to ensure that as long as the code is exactly the same, the decisions that will be taken will always be the same. But as soon as we change a little bit of the code, or we change the key, the decisions will be completely different. And since the decisions will be different, the resulting code will diverge vastly from the original one. Same thing with the split transformation and with all the other ones that entail random order of the code, randomizing the order of the code. So that is basically what this framework allows you to do. Instead of just saying, I want to obfuscate this function, you just provide a obfuscation key that is used in order to decide what will be done exactly. The second problem we have is that, well, you can always reorder the code to find the original change and see where you want to look at. But obfuscation is basically trying to, well, make that a lot harder by making the attacker spend a lot more time figuring out what the code actually does. There is one more problem here, and that is that if your original code is not obfuscated, and the patched code is, the attacker will still be able to figure out what was changed by looking at the original code. They just need to see which of the functions were modified. So that is why it's really important to already provide obfuscated code if you want to use a technique like that, so that the attacker will not be able to figure out what the original code did is exactly and what the new code did exactly. And that is why we obfuscate only specific parts of the function, as in, if you change the obfuscation key for a specific function, then that function will change, but the other ones will remain constant because they will have the prior obfuscation key. This is done by adding marks to the functions when you are compiling, for example, with clang, or you can provide this as a parameter to the modules. And well, that is the reason why we choose to do this with LLVM, basically, that you can do that really, really well, as you can do that for a lot of languages, and you have a lot of good frameworks and a really clear intermediate representation. So you don't need to do that for exactly each one of the target hardware architectures. The problem you have with this is that you cannot be as creative with obfuscation as when you are writing your own assembly directly. But on the bright side, it's a lot simpler if you can just pick 20 programs, put them in your compilation pipeline, and get 20 obfuscated programs instead of having 20 people trying to write obfuscated code for each single one of them. And well, this is, for example, how you could use my framework if you wanted to obfuscate the code. So first thing you do is that you just compile the code with clang and generate LLVM code. And here you can just see that we are just randomizing a little bit the different parts of the code, and we are just doing some obfuscation transformations. But this will not work well, and instead we have more something like this. So yeah, this is a little bit more like it. Basically, what we are doing here is that we are loading the obfuscation library. Then we are just adding the module key. This key is representing what the obfuscation key for everything that doesn't already have an obfuscation key. For example, we can have a function with a obfuscation key, but we might not have defined obfuscation keys for every function, and we want still obfuscation to happen on all of the functions. So that is why we have this. The propagate module key will pick the module key and apply it to every single function that doesn't have any obfuscation key. Then we are just applying the split transformation, and as you can see, there is a probability of 1 to 8. Then we do the control flattening transformation, and we do that before the constant obfuscation because the control flattening will generate a lot of new constants that we want to actually obfuscate later. The probability of obfuscating constants, as you can see, it's a lot lower than 1 to 2, because if it's higher or equal to 1 to 2, you might end up with a very large stack, and eventually your compiler will crash. And finally, we just do the randomization functions because they are really, really simple to do, and they don't have any prior dependencies. And finally, we just compile the resulting code. So you can take this as an example. I can probably show you some obfuscated code. These are probably the two links if you want to read more about my work. On the bottom side, you will find the LLVM version modified to do obfuscation. And on the top is my master's thesis. So let's see if I have some interesting code to show you, but I don't think I brought it on this laptop. Sorry. Oh. The funny thing is, CD, let's see, it should be my LLVM. Oh, here it is. So you get an idea. The original code is this one. This is a real, wrong side, there. So as you can see, this is basically a reasonable simple case of read your name and then say hello and your name. But when we run the obfuscation code, and if I recall correctly, it was this one, then here you can see that when we go here to the start function, we don't have such a clear view of what is going on here. So, wait, no, that is not the main function, should be, here it is. So here you can see that the code has been significantly obfuscated. The order of the functions doesn't make so much sense, and there is a lot of cross dependencies. It's only the function calls that make things have a little bit more of sense. So, for example, this XOR that you are here, no, not this XOR. This mob that you are seeing here, if I recall correctly, it's one of the obfuscating functions. And here you can, no, this is not obfuscated code. Okay, then I'm sorry. I thought that this was the obfuscated code, and no, that is not actually it. Then I suspect it's not on this computer. Well, then we are going to have to leave the talk here. If anybody wants to see an example, please come by and I will show it to you in a more private way without the camera recording.
Have you also made the complementary to try to de-obfuscate it as well?
Yes. Yeah, I will repeat the question. He asked me if I have developed a tool in order to try to de-obfuscate this code. I didn't have enough time when I was doing my master's thesis for that. But if you read my master's thesis, you will see some interesting ideas that I really wish someday I will be able to develop. Basically, I explained that, for example, for control flattening, you cannot fully reverse the obfuscation technique. But there is nothing preventing you in order to have an heuristic that allows you to put an order to the original function so you can compare both of them. So if two different functions are using control flattening, you can still try to figure out which is the difference between one and the other by putting one to the side of the other and seeing which is the specific blocks that have been changed. For randomization functions or randomization of instructions, you can always have the order decided in a similar way.
One thing that is easy to figure out when you're trying to de-obfuscate some code is, for instance, if you have a lot of strings and then de-obfuscate a large Java blob that where they had a single function with one argument that was actually callable from outside the jar file, so I could just make a small function that called into it. I didn't even have to re-implement it. And then I could take all, and that function was always only used with one single string as an argument, and that was where all the strings in the code was. So by passing all the strings into it and replacing it in the object code, I could get all the real strings back. And then it was quite easy to figure out that, oh, this first if statement in the top of each method, where it just checks this variable, and if it's not this, if this just does not variable, and then it has an error with not initialized. It's quite easy to figure out what that constant was. So there are a lot of patterns in the code which makes it easy to figure some stuff out.
Well, when we try to approach that other technique that you are talking about, which is basically obfuscating of constants and so on, we also considered that actually optimization passes are the worst possible enemy that you can have when you are obfuscating your code. And the reason for that is because optimization passes are really, really good at figuring out what is constant and making it back into a constant again. So you could probably try to use an optimizer in order to try to solve some of the problems you were seeing with the constants. The main issue, as I said, is that I didn't have enough time to basically develop this into a project of itself. So I'm not sure if that is answering or giving you a tip on which direction you can look. Okay, any other questions or anything?
Yeah, from my side. I know of a master thesis from 2015 from a student in Munich, I think, who developed very similar things. Also a set of transformations for AR and LLVM, but both for obfuscation, but also for reliability and basically defense skills. Do you know that? For defense, like attack defense capabilities, like, okay, you have also some stack protections in there and so on and so on. Do you know that master thesis?
No, I don't know about this, but mostly because this master thesis was originally presented in 2015, actually.
Ah, okay, then.
Yeah, so
okay, yeah.
It was really fun because when I started this master thesis, there was absolutely no interest on the area. There was basically nobody working on it, and it took me like 2 years to finish the master thesis. So when I finally presented, all of a sudden, there was like a blooming new field of obfuscation technologies and so on. And I even found an LLVM obfuscator that was like, oh, if this had existed when I was doing my work, I probably could have been able to save like 3 or 4 months of work. Okay, is there any other questions?
I think not. Then thanks a lot for your talk.
Thanks a lot for coming.